Thanks for everybody who's already here. We're going to get started. And I'm Karen Lightman. I'm Executive Director of Metro 21 Smart Cities Institute at Carnegie Mellon University. And we really love to host these lunch and learns. They're a great opportunity. We usually do them in person, but sometimes they're virtual. And I think we're all getting more used to Zoom and Zoom fatigue. It's a way to find out what's happening with respect to our definition of smart cities. So at Metro 21, we take the 21 is the use of technology, 21st century technology, and applying it to real world problems. And we do that in collaboration with our municipal partners, as well as the communities that are impacted. I'm so thrilled to have Destenie with us today. Not only is she like the coolest person ever who hangs out in hammocks and teaches her PhD students, but she has a really illustrious career before she has come to join us at Carnegie Mellon. She's an adjunct professor in civil and environmental engineering and a presidential postdoctoral fellow in the Department of Engineering and Public Policy. She received her PhD from the University of Massachusetts in Amherst. And you did, let's see, there you did systems modeling and analysis in New England and sub-Sahara Africa, which I know you've been to, which is so cool. And today she's gonna talk to us about power systems. And this is a lunch and learn. So we definitely want you to, if you have questions, pose them here. I'll play moderator. And I'll, I don't know if Destenie, you can see them, but I'll make sure that you get the questions and we'll take it from there. So with that, Destenie, the floor is yours. Thank you.
Thanks. And just to clarify, the difference on the slide with it saying assistant professor is I officially become assistant professor in August. So
okay,
temporary positions right now, but I am moving.
16 days.
Yes, 16 days. So in this talk, I'm going to detail a method that I created for evaluating a portfolio of generation technologies in terms of their sustainability and in having like holding reliability as a constraint. And then we also integrated preference scenarios to get a sense about how different decision makers would change their view of the quote unquote most sustainable power system. So when I think about energy planning, I think of it as a tool to increase social benefits. And that can come of one of two ways. Either you're thinking about increasing overall system sustainability, which is typically what we think about in more developed countries like the US, reducing air pollution emissions, et cetera. And in developing countries, you might focus more on increasing electricity access because you view that there is a link between electricity access and human development. So in the first part of this talk, we're going to be focused on increasing overall system sustainability. And this is really going to focus on the New England power system. That's where I started my research in power systems. And so if you have no idea where New England is, it's in the upper northeast quadrant of the United States. And it's made up of Maine, Vermont, Connecticut, New Hampshire, Massachusetts, Rhode Island, and yeah, that's all of them. And they have a lot of energy questions that they are going through. So they were retiring about 5.5 gigawatts of coal and oil capacity, and 3.3 gigawatts of nuclear was at risk for retirement. So the main question that we were asking in this analysis was, which combination of power plants is going to be the most sustainable in terms of reaching their goals? So if I asked you, what's more sustainable, coal or wind? A lot of people would just respond immediately with wind. And the same thing goes for natural gas versus solar. Often in the audience, then a lot of people will respond with solar. But if I was to ask you, what's more sustainable, a grid that's 50% natural gas and 50% wind versus a grid that's 50% natural gas and 50% solar, there would be more difficulty in understanding that. You need to understand your definition of sustainability, and you also need to understand your resources and how much energy each generator will contribute. So that makes a great motivation for a sustainability model. So in the past, there have been a lot of these sustainability studies that have looked at individual technologies. So Maxim 2013 compared 14 technologies across 10 sustainability indicators in a global context. whereas Klein and Willey, they compared 13 electricity technologies across 8 different preference scenarios for the USA. And here I think Klein and Willey had said that geothermal was the most sustainable. And biopower was also ranked really high in terms of sustainability. But one of the downfalls of these analyses is that no single technology will ever be used to run the entire power system due to security concerns and resource availability concerns. So the main kind of thought behind this was that the sustainability of the whole power system is not necessarily equal to the sum of the sustainability of the parts. So to answer this research question, we kind of based our analysis on the resource adequacy problem. So ensuring that enough generation capacity satisfies demand, given the large-scale commercial technologies in the New England sector at the utility scale. And so New England is, really dominated by natural gas. It's about 44% of their grid. They have a lot of hydro and nuclear plants. Wind and solar farms are, becoming really largely deployed, especially with offshore wind technology making its way into the US market. And then the peaks are satisfied with oil plants that often come online in the winter when the natural gas is largely being used by the heating sector. So in our initial analysis, we abstracted from transmission constraints, which means that this is going to be a lower bound on generation capacity needs in the New England region because we are not going to account for things like congestion, for example. So that's a great, that we're leaving that for future work. So when we're looking at our methodology that we're using in this paper, the green boxes are where we're going to be defining the portfolios. So first we start with gathering data on the hourly demand and wind speed information across the New England region, as well as solar radiation data and nuclear outage information. We input our initial generation capacity levels. We feed this information into an electricity model. Then once we run the electricity model, which I'll explain more on the next slide, we determine if that generation portfolio is reliable, meaning can it meet the demand that we have set based on historical demand constraints for every hour over a 5-year time period. If it's not deemed reliable, we have to add capacity and then we'll rerun it through our electricity model until we reach a reliable portfolio. And once we reach a reliable portfolio, we output the energy by source, and that feeds into our sustainability metric calculation. We have established preference scenarios, which we've taken from the literature to represent our different decision makers, and then we'll rank those portfolios based on the different preference scenarios. So the blue boxes are where we're defining our portfolios or the mixes of energy technologies, and the yellow is where we are actually evaluating the sustainability of these different portfolios. So this is our electricity model. It's a merit order dispatch model based on historical prices in the New England region. So we start at time t with our hourly demand, which is going to be abbreviated for HD. And we dispatch nuclear, because often it's negative in the New England region. We then dispatch solar and onshore wind, followed by offshore wind. If there's still hourly demand left, we'll split between natural gas and hydro. And then we have to check if the pipeline is maxed out. So in the New England region, natural gas has to go to the heating sector first. So if the pipeline is maxed out, then we believe that we are in winter due to the heating demand constraints, and we'll dispatch oil followed by hydro due to needing to keep the river level higher so that we don't have a large amount of fish impacts. If the pipeline's not maxed out, we'll dispatch hydro first, followed by natural gas, followed by oil. And if after we run through all of our technologies in the model, we still have hourly demand left, then we say that we need capacity and that portfolio is not able to be tested any further in our study. And if we don't have any hourly demand left, we keep running this portfolio through our 5-year simulation for every hour of the year. So,
Destenie, it looks like you have a question.
Okay, I can't see any questions, by the way.
I will read it for you. Why are nuclear and onshore wind dispatched first? I think that's a good question there.
Yeah, so nuclear often bids negative in the market. So it doesn't want to turn off because if it cycles up and down, then this can really impact its like fuel rod controls, which if they melt, then you have a nuclear explosion. So it's real, they love to keep a constant baseload. And then onshore wind and solar still have a lot of tax credits in the New England region. And so they're able to bid lower than offshore wind in like based on our LCOEs that we were getting to make this model.
Very cool. Thank you. So there's some policy decisions that have been made in the New England area to help prioritize where they want the energy.
Yeah, so right now, like solar and onshore wind are low enough that they are seen as a negative load or a must take in the New England region. So if they were actually competing in the competitive market, then we would actually need to capture like how the prices would change over time.
Thank you.
Mm-hmm. Okay. So the outputs from the model can be seen here. So in the solid bars, we have our capacity in gigawatts, and the fuzzy bars would be the output of the dispatch simulation model that are going to show like energy contribution by percentage. And green represents offshore wind, yellow is solar, the purple at the bottom, it's really small because most of the onshore wind in the New England region is in Maine, but not in Massachusetts, for example. And so the blue is hydro, the gray is oil, and the red is nuclear. So some of the things that we were focusing on with these portfolios is what's the role of nuclear in terms of sustainability. So you see in portfolios 1 through 3, we have completely eliminated nuclear. In portfolios 4 and 5, we have assumed that maybe in the future nuclear would become favorable again in the New England region. We also have a lot of portfolios where we've kept the base level of nuclear, assuming that they keep their current capacity and they don't make too many changes. We also asked the question of which generation should we use to support high offshore wind penetration. So you can see in portfolios 6 through 10, we have really high levels of offshore wind in the New England region. So this is about 10,000 megawatts. And we have been supporting that with different mixes of natural gas and hydro and oil capacity. Our sustainability model is based on the multi-criteria decision analysis framework, or MCDA. The step 1 is to identify different alternatives. So that would be the different portfolios in our analysis, and also to identify sustainability criteria, which I will tell you on the next slide. Then in step 2, we calculate the criteria scores based on the projected energy contribution from our energy model. We normalize those scores between 0 and 1, with 1 being the best and 0 being the worst. That way we can compare across different criteria. We'll assign criteria preference rates, which indicate the relative weight of importance of each criterion compared to the others. And then in step 5, we're going to rank the alternatives. So in the sustainability model, we considered 7 sustainability criteria. The first is economic, with the levelized cost of electricity. We also included environmental constraints, like concerns like life cycle greenhouse gas emissions, life cycle air pollutants, land use, and water use. And then on the social side, we included fatalities, expected fatalities per gigawatt hour, and jobs as a full-time equivalent per gigawatt hour. When we are determining the portfolio scores, we acknowledge that each power plant will have a fixed impact for sustainability and a variable impact. So what I mean by fixed impact is these are the emissions that just come from building the power plant. So for example, with an oil or natural gas plant, there's a lot of concrete involved, which is very CO2 intensive over its lifetime. You also have CO2 emissions from drilling to get the oil, which would be more on the variable side. So the variable side is just any emissions that come from operating those power plants. So in our equation, the Zij tau is the sustainability impact of technology tau on metric J in portfolio I. And the fixed value for sustainability of technology tau on metric J is going to be divided by the hours in the year times its capacity factor, plus the variable emissions. And so then to get the entire sustainability sustainability score for portfolio I on sustainability metric J. We have to sum the individual scores for each technology, and then we will multiply that by their contribution to meeting the energy needs in that portfolio. And then this table just lets you know if we have determined that the metric is completely fixed, completely variable, or a combination of the two. Okay, so these are the outputs of our sustainability model. So the x-axis is the sustainability score. And so a longer bar means a higher sustainability ranking. Along the y-axis, we have our different energy technology combinations, and the grayish purple is the cost metric, the LCOE. Red is greenhouse gas emissions, green is air pollution, purple is land use, blue is water consumption, orange is fatalities, black is jobs, and the red striped bar at the end lets you know how the ranking of the portfolio changes if you include nuclear version. So what I mean by nuclear version is we can assume that some decision makers or stakeholders will be really against nuclear. So if all you cared about, or if one of your sustainability metrics was to just get rid of nuclear due to the perceived risk that you have for having nuclear, like having your nuclear fleet, then this would be how you changed your score. Oh, I see a raised hand that's flashing on my screen.
See, I think I can ask her to unmute and she can ask a question. Nina.
Hi. Yeah, I was wondering
great.
if the goal is to have a low sustainability.
The goal is what?
Hard to hear you, Nina.
Lower sustainability score. I'm just kind of confused because I would think like you would want these bars to be lower, right? Or maybe I'm misinterpreting the graphic.
Right, so a longer bar is more sustainability. So for LCOE, lower is better. So it's the inverse of the bar. So if it has a sustainability score of 1, that means that it was the lowest cost portfolio in our analysis. And if you have
portfolio 3,
Great, thank you.
You're ranking it in terms of right here. So portfolio 3 would be the quote unquote best.
Yeah, so actually it's portfolio 12 because it jumps right up to 1, right? So it has a score of 1, meaning that it's the best portfolio in terms of cost for our entire analysis, right? And that means that this is going to have the lowest cost.
Okay.
There is a portfolio, so portfolio 10, it has the lowest bar, meaning that it has the highest cost. So it's inversely proportional. The only one that I guess like longer is, so it's directly proportional would be jobs, because more is better, right? So 1 for jobs means that it has the most jobs, and a 0 for jobs means that it has the least jobs. So with this graphic, we noticed some things about some trends. So we see that portfolios 6 through 10 are all the high offshore wind portfolios, and those ones are all towards the upper, in the upper quadrant of our bar chart. And portfolio 4, the number 2 portfolio, when you don't include nuclear version, is our high nuclear portfolio case. And it scores well because of the low greenhouse gas emissions and low air pollutant emissions from nuclear. I mean, also nuclear has a very high energy density, so you can just get more production out of it for less land use compared to other technologies. And we see that our portfolios without any nuclear, so portfolios 1 through 3, fall to the bottom half of this graph, particular portfolios 2 and 3, and that's because they score really bad on air pollution emissions and greenhouse gas emissions, because they have compensated the retirement of nuclear with natural gas capacity. We do notice that portfolio 4, if we included nuclear version, so these red fuzzy bars, portfolio 4 would actually fall more closer to the bottom half of this. So if we assume that in the future, decision makers might have, we might have another nuclear crisis, or if we have decision makers that are very averse to nuclear, then we would be more kind of like unwilling to include this one in our top 5. depending on the stakeholders that you have. And then another thing I do want to point out is that I've given every sustainability metric an equal weight in this graph. So because I have more environmental criteria, and inherently we've given the environmental side of sustainability a much higher precedence over the economic and the social side, because everything's weighted equally. And then if we don't include nuclear aversion, the only portfolio that we found to outrank portfolio 9, so the difference between portfolio 6 and portfolio 9 is that 9 has a higher amount of nuclear. It's kept on its base capacity and added a couple of nuclear power plants. So the only time portfolio 6 outranks portfolio 9 is when the nuclear capital cost exceeds $7,000 per kilowatt hour, or the natural gas air pollution emissions fall below 500 milligrams per kilowatt hour. So if, for example, they had like some carbon capture technology attached to these natural gas plants, then portfolio 6 would continue to rise in the ranking. One of the things that you might be saying is, well, you know, it's kind of rare for decision makers to care about everything equally all the time. So how would the ranking of the portfolios change when you look at these things pairwise? So this is a scatter plot matrix comparing the sustainability criteria. Each dot represents a different portfolio, and the red dot represents portfolio 9, which was the most sustainable portfolio when we rated everything equally. The way that you read this is you look at the intersection. So if you wanted to know how the portfolio is ranked when you only considered air pollution and land use, you would go to the intersection of these two and you would look at this box. Same thing for air pollution and water consumption. And then you would look at the intersecting box there. One thing that we see, so the red highlighted boxes indicate that a strong positive correlation between our metrics indicates that we could actually reduce the number of criteria that we're considering or presenting to decision makers. This also lets us know that, so let's say, for example, we had a decision maker that really cared about reducing greenhouse gas emissions, and another decision maker that really cared about reducing fatalities. So if you actually talk to them only in the metrics that they truly care about, you would actually end up seeing the same most highly ranked sustainability portfolio in both cases. So it actually just kind of helps you think about how you can talk to people. The same thing goes for nuclear consumption, nuclear aversion, and water consumption. And then if you look at the pink box, when we have a Pareto frontier or a non-positive correlation, we get we understand the trade-offs between portfolios. So if you're looking at the intersection of air pollution and jobs, where my mouse is, then this trade-off here between the red dot and this non-highlighted dot would actually let you know if you move from portfolio 9 to, let's say, portfolio 5, how many air pollution emissions are you having to increase the number of jobs? Is it going to be, 10%, 50%, for how much job gain, 20%, 30%, et cetera? And so this kind of helps decision makers understand what they're winning and losing on when they move between these two different portfolios. So kind of just understanding what's the difference between the best and the second best and the third best. So then when we wanted to kind of think about how different decision makers would rank these portfolios, we decided to look at preference scenarios. And so these we actually took from the literature. We did not make these up ourselves. And the bold number represents where the decision maker has given the highest weight. So along the y-axis, we have the different decision makers. Along the x-axis, at the top, we have the different sustainability criteria, and then the numbers represent the weights of importance. So for example, with the climate change decision maker, we assume that they've given 90% of what they care about to the greenhouse gas emission criteria, and then 1% of what they care about goes to everything else. And then we've changed these rankings to represent different stakeholders. So when we include this in our analysis, we actually find that we can actually eliminate a lot of our portfolios. So in total, I have presented about 15 portfolios here to you. But in actuality, we tested about 35 to 50 different electricity system combinations in our analysis. But when we included the stakeholder preference scenarios, we actually found that we had a non-dominated set of 7 portfolios. So when you include everybody's and what they care about, this is kind of like the best ranked ones. And so here we see that portfolio 9 and 4 are scoring really well in the majority of preference scenarios, except for when you get to the economy, and that's going to be because of the high cost of offshore wind and nuclear. The jobs is low in the nuclear case because, again, nuclear is very energy dense, and so you won't need to hire as many people in theory. There's some kind of limitations with getting jobs from energy output, so that should also be taken into account. And then when you combine the jobs and economy. And then we looked at which, if any of the portfolios would become non-dominated. And the only one that would kind of jump into our non-dominated set is portfolio 1, which is a portfolio where we completely retired nuclear. And it becomes non-dominated upon just a 7% increase in nuclear capital costs, because that kind of drives a lot of these portfolios down in terms of the economic preference scenario. And then portfolio 6 becomes non-dominated if you increase the nuclear costs by 100%. So if they became really expensive, like we kind of saw in Georgia and South Carolina a couple years ago. And so then we can ask ourselves, well, we have those equal weight portfolios, but how would things change if we included aversion to nuclear in our equal weight preference scenario? So along the x-axis, you have the nuclear aversion scaling coefficient. So as you increase, so at the beginning in our initial equal weight, we had 0% of caring, and then you have 20% of what you care about is nuclear aversion, and so on. The green lines are representing our high offshore wind cases. The orange lines are representing the cases where we've completely retired nuclear, and the pink line is where we have increased nuclear capacity. So what we see from this is that if you are going to have a strong preference against nuclear, or you think, or the stakeholders believe that in the future they could have changing preferences toward nuclear, towards increased nuclear aversion, then you probably would not want to start off in this portfolio because it's going to fall very quickly. So this portfolio 9, once you kind of reach the 20% to 30% mark, the portfolio in terms of its sustainability falls fairly quickly. So then actually choosing our 3rd best portfolio would provide you with some robustness to the nuclear aversion criteria. Oops, I kind of said that. And so I guess I can pause here to ask if there's any more questions about the New England side. And then I'm going to move into my work on increasing electricity access, which is based in developing countries.
Okay. Can I just ask, I want to ask a devil's advocate question. So just help me understand, because nuclear is like a really, people love it or hate it, that kind of thing. Yeah. Tell me why you're thinking, well, what's the reason and rationale behind saying that nuclear is not sustainable? Because of, I think it was the impact, or what's needed to build a nuclear plant, or can you just explain that a little bit?
I think the main place where nuclear doesn't do well is in the cost side, because the costs are so expensive. So economically, it's ranked really low in terms of sustainability. So in South Carolina and Georgia, they were building nuclear plants, and last I checked, they were like a couple $2 billion over their budget. And so it's just really expensive to try to build these nuclear power plants, because you have to, also make sure that you are taking into account your radioactive concerns, your safety concerns. I know that small modular nuclear reactors has kind of like resurfaced, and a lot of people are looking into that technology. I'm not an expert in small modular reactors, but I think that the economics is a lot of times where I hear people have the biggest sustainability concern. And then there is also, you know, the risk, the low probability, but very high impact risk.
Great, thank you.
Okay, so now I'm going to talk about the work that I've done in Sub-Saharan Africa, where we're focused on increasing electricity access. So this work is published in Applied Energy, and we are calling it Changing the Policy Paradigm, a Benefit and Maximization Approach to Electricity Planning in Developing Countries. And in this paper, we propose a method for incorporating stakeholder preferences towards equality into an electricity planning framework. The motivation behind this is the United Nations 2030 target for universal access to modern energy. And the main question we were asking in this research is, what should universal access look like, and what does equitable universal access look like? The reason we focus in Sub-Saharan Africa is because there is still a large part of the population that is completely without access to electricity. So for example, in Ethiopia, you have 76% without access to electricity. In Liberia, where this work is based, we have 98% without access to electricity. And you can see how the dark blue parts of these pie charts are varying, particularly once you get below Northern Africa, except for South Africa, and they're really oil-based. So when I think about injustices and equality concerns in the energy sector, I really think about them in terms of 3 different scales. The first is the micro scale or the local scale. So this would be environmental impacts and concerns. So for example, exclusion of rural areas from benefits. In this picture, you see 2 rural huts that are literally under the power grid. They don't have electricity access in their home, and we call them undergrid, for example. And so these might be, you know, prime candidates for decentralized technologies such as solar home systems, or I know that solid oxide fuel cells are emerging as a technology. And so deploying distributed generation would be really valuable here. We also have the global scale or the macro scale. And so that deals with the extraction of materials and the waste streams. So who's having to deal with the waste? You know, how is that impacting their environment? Those types of things. And lastly, we have the mesoscale, which focuses on national issues such as unequal access to renewable technologies. So for example, in this picture, you are seeing that some houses have solar panels, others do not. And so this could also deal with the inability of certain communities on a national scale to purchase low carbon technology. And we're also considering looking at increasing electricity prices as an equality concern at the national level. So when I think about electricity access, I actually think about it in terms of 5 facets. First, we have the quantity or the amount of electrical supply you receive. This means like how many appliances can you connect in your house if you have an electricity connection. The affordability is what percentage of your income you spend on electricity services. Reliability is the number of disruptions that you receive towards your electricity supply. So, you know, in the US, you might experience an outage once a year or a couple times a year. But in developing countries, we're really thinking about the number of hours per day or per week. And then the quality is the voltage level. So that's going to be when you plug up your computer, is the electricity voltage level going to actually ruin your appliances? So as an example, when I was in Ghana, my phone battery would always overheat. And I'm sure some of you guys have experienced maybe your laptop overheating. And sometimes that's an indication that the voltage level is not properly rated for the battery in your appliance. And then lastly, we have the supply side. I highlighted in green because that's where the model focuses. And it's focused on, is there electricity supply in your area? So that's the distance that you need to walk to get an electrical connection. Is it in your home, a community center, or down the street? So when we're thinking about turning these concerns into a model, in the developed world, the situation is often that the grid is well developed, access is unlimited, and the system is considered reliable. So then that optimization problem becomes to minimize the cost subject to demand, reliability, and environmental constraints. But in the developing world, often the situation is that the grid is undeveloped and access is very limited, meaning that the system is also unreliable, meaning that there might be hours of outage per day, and the demand could also be unknown because people typically haven't had access to electricity. So then the problem becomes to maximize the social benefits subject to a cost, because often there's a lot of donors that are helping to build this system. So when we estimate social benefit, we use the Human Development Index, or HDI, which is a composite statistic developed by the United Nations that reflects life expectancy, education, and per capita income indicators. Along the x-axis, you have the per capita electricity consumption in kilowatt hours per person per year. Along the y-axis, you have the Human Development Index, and then each dot represents a different country. To give you a sense about where the different countries are, we see that developing countries are below the knee of this curve, and the more developed and oil-producing countries are up upon the saturation effect, or the logarithmic tail of this curve. And so while we acknowledge that this is a correlation, not a causation, you just don't see countries that do not consume a high amount of per capita electricity consumption with a very high human development index. So we are using this as our base level for equality, saying that if we had a decision maker that really valued an equal system, this curve would represent their belief system or their preference. This is the, so I promise not to give you guys too many equations, but this is the main objective function that we use in our optimization model. So it's to maximize the utility or happiness derived from potential electricity access. And the utility is that U, and the X is going to be the electrical energy that can be delivered to a location or node I. And the P is going to be the number of electrical consumers in each node. So we kind of see that displayed here. I will just say that we are looking at this utility as a function of the per capita electricity consumption in each location that can be consumed by the consumers. We coded this as a mixed integer linear program solved in Groby and Python using a linear approximation for this nonlinear objective function. And alpha is going to be the equality preference. So that is the alpha is going to be what we use to change the concavity of that curve for the Human Development Index that we had showed. And so, for example, a alpha of 1 is going to be a very strong preference for equality. An alpha of 0 will indicate that the decision maker doesn't really care about equality. They only care about maximizing the electrical consumption in the country. This is a flow of information diagram to kind of help you conceptualize how the model works. The inputs include the social planner's preference for equality, budget constraints, and geography constraints, as well as population, generation costs, and transmission costs. Inside of the model, so inside of this dotted line, the model will determine where they build power plants, so the generation investment, and where they build transmission lines. This feeds into a calculation of how much electricity can flow around this system, and that goes into this power flow calculation. Based on the power flow calculation, the model will determine how much electricity to leave in each location, so the electrical consumption. And these will feed into the costs in the system, which runs up to our main constraint, our budget constraint. And the green circle is representing our objective function, which is the social welfare or the utility that the stakeholder gets for bringing electricity access to their country. These are our main constraints that the model is using. I will say that these are not the only constraints, but for time considerations, I cannot detail the entire model or the code. The budget constraint is a mixture of the transmission costs plus the generation costs and less than or equal to our set budget. The electricity availability or power flow constraint is going to be the electricity at node I has to be less than or equal to the generation at node I plus the flow of electricity into the node minus the flow of electricity out of the node. And then the generation constraints are saying that the total electricity generation at node I has to be less than or equal to the sum of all generation technologies at the node. And then we have other constraints that I will be happy to talk about later. Our initial case study is Liberia. And so as I had pointed out before, that Liberia has a very low amount of electricity access, as seen in the pie chart. 81% of the country at the time of starting this model did not have any type of access, and only 5% were connected to the Liberian Electricity Corporation, which is their main power grid. Then other people who had electricity access might have a community generator, a vehicle, battery, or some other type of source. And then the map on the right-hand side is a population density map. And so the bigger the circle, the more people live there. And so the big circle is Montserrado in the northern part of the country, and that's where the capital city is. So this is an output of our maximized energy access model. And so on the right-hand side, we have a $5 million annual budget, and on the left-hand side, we have a $10 million annual budget. This, in both cases, we have started off with the high equality preference of alpha equals 0.86. And we are showing how the decision for where to build power plants changes as you move across budgets. And this is also assuming that this annual budget is invested for a 30-year time period. So this is the grid that you would have after 30 years. In both cases, we see that the model chooses to use the existing hydro plant, which is the blue diamond, and they use low voltage transmission lines to expand the power system, so the green lines. Then when we double our budget, we see a larger deployment of solar, PV, and diesel mini grids, which are the yellow diamonds. And anytime we have any budget left over, but not enough to build a new power plant, then we see a yellow dot, which is going to be a deployment of solar home systems in mostly rural communities.
Hey, Destiny, we have a question.
Mm-hmm.
Is it possible to call out the impact on women and girls? There are a significant amount of capital from available to focus in on social equity in this area.
So I think to call out the impact on women and girls, I don't know how you would do that at a really high level national model like this, because I'm not modeling like households, for example. So I could think about getting how many women and men live in each of these different locations, but I think to really get an impact that these electricity systems have on women and girls, I would need to understand what these electricity systems are being used for. So I've estimated household or residential electricity demand and built a system to match that. But I haven't estimated how much electricity is being used for cooking, how much is being used for lighting, how much is being used in, to help them with their cleaning or something like that. And so then, it also depends on what type of equality concern you are considering for women and girls, right? Is it reducing indoor air pollution, reducing the, increasing their ability to work outside the home, that type of thing. So that's a very loaded question, but yeah.
Yeah, it sounds like a separate thesis, but I think it's an interesting idea that if there's more energy, then it can help liberate people who typically would do those in-home activities that take a lot more effort if there's no energy. You can't run a dishwasher, for example.
Right, and so there is some literature on how these energy systems or electrical systems can kind of reduce the impact on cooking, the time it takes to cook with clean cooking systems. But there's also some people who kind of acknowledge that culturally there is not a large incentive to change the method of cooking, because there are certain dishes that need an open flame, right? And people just like the taste, right? If you cook on a barbecue, it tastes really different than if you cook in your house. And so then there's also talk about deploying systems where you just put a fan in the roof of a house to just take the smoke out, right? And so those are two different things that can both reduce air pollution within the home and change the air pollution that you experience with cooking, but they have very different energy concerns and demands.
Cool, thank you.
Mm-hmm. So if we look at this moving from 10 million to 50 million, we actually see a large deployment of centralized grid capacity. So, in our 10 million case, we see a lot of solar PV diesel mini grids. And then in the 50 million case, we see a lot of like hydro and oil power plant deployment. And one of the things that we have noted for future work here is that if we had a completely off-grid system that had a higher capacity factor than solar diesel mini grids. So for example, if solid oxide fuel cells became much cheaper, then you might see a more combination of decentralized and centralized power generation infrastructure here. But because we are modeling it at such a high level and not the household level, our model will be biased towards centralized generation capacity. So then you can also ask yourself, well, how would things change if you had different equality concerns? So on the left-hand side, we have a low preference for equality, or alpha equals 0.10. And then on the right-hand side, we have the high preference for equality, which you saw in the previous charts. And so on the left-hand side, we see that when the decision makers do not care at all about equality, we actually have just kind of built their existing power system. You have very large power plants near the capital city without connecting a lot of the rural consumers. And in the high equality preference case, you've used the existing hydro plant, but you have not used the existing oil plant, and you have dispatched a lot of decentralized generation, which Liberia has been talking about doing. So one of the main takeaways that we see from this model is that you need to care about equality at the forefront, and the main trade-off that we're seeing between caring and not caring is an investment in infrastructure, so transmission infrastructure and decentralized infrastructure.
Thank you. We have a question about the equality preference, and this one is, how was the impact to nature, such as forest, agriculture, indigenous peoples' lands, included in the infrastructure investments and equality preference? She's curious, or Ling is curious, because working with the UNDP this summer, and they're developing a country spatial map to identify areas for livelihoods, such as water security.
Okay, so in this initial part, we did not include environmental concerns. So you can imagine, like, we are assuming that the only thing that a decision maker care about is meeting their budget and their view of equality. But on the back end, so I'll skip to this side. So we tied this with a multi-criteria decision analysis assessment to understand how equality and development concerns linked to environmental sustainability. The three sustainability concerns that we were thinking about were droughts and water use, air pollution, and scalability and variability. And we were looking mostly at greenhouse gas emissions and water consumption for the 4 technologies that we included. So this is kind of metrics that we got from the literature. These are averages, and currently we are working to expand this to include a wider range because we know that life cycle assessments vary widely by country. But when we looked at the averages, we saw some distinct sustainability trade-offs between different alphas and different budgets. So, so along the x-axis is the different things that the decision makers would care about. We use per capita electricity consumption in the country to represent development. We use the equality, which is the Gini coefficient. So a Gini coefficient that's lower is actually better, so it's inversely proportional. And then we have CO2 intensity of the system, so CO2 emissions per megawatt hour, and then we have water intensity of the system, so liters per megawatt hour.
We have a question. Ooh, yeah. Ooh, sorry, finish your thought.
Oh, okay. So the colors represent the different budgets, and the colors represent the different budgets, and the symbols and the solid lines all represent the high quality preference case, and the dotted lines represent the low equality preference case. So let's just take the budget of 10 million, which are the 2 blue lines and the circles. And for the high quality preference case, we see that we're not as good on the electricity consumption because we've now taken some of that value and invested in transmission lines as opposed to larger power plants. So we do really good on equality, but we do really bad on CO2 emissions, but we're doing great on water consumption. So one of the things that we noticed was that, with this low CO2 score, we saw that there's a higher amount of solar PV diesel mini grids. Oh, I think that's this one. Yeah, so it has the most mini grids. And so using a lot of diesel actually causes this one to do worse on CO2, but better on on-site water consumption because we haven't, dominated our system with hydro capacity. And then for these other ones, they're very hydro dominated. And so one of the things that we need to include is a more detailed analysis on the limitation of the water resources in Liberia. So we would need a higher kind of resolution to look at flow streams and estimate the power that can be stored in that water based on how much dams you build.
Well, this was actually a related question. She's asking, was micro hydro considered in the model? The World Bank had a micro hydro project in Liberia a few years ago in rural areas.
Yeah, so we allowed the hydro to, I think the initial capacity that you had to build for hydro was 5 megawatts. So the model can choose to build between 5 megawatts up to, I think, 100 megawatts, but I would need to double check that.
Thank you.
You're welcome. Okay. So let's talk about that. So for future work, some of the things that we were thinking about were that this development question is really a multi-period optimization. So we've focused on equality preferences. So building generation where you think that you're going to have the highest distribution of electricity access. But so if you move from 2020 to 2040, then in the future, developing countries are going to have to take on the cost of running their own system. So while they may start with these high preferences for equality, we also need to look at, in the second stage or 20 years down the road, then designing this as a cost minimization where they have to decide investment in generation and transmission constraints given their own in-country budget based on the demands that they're seeing and the existing grid that they built based on their equality preferences. We also have talked about including air pollution emission constraints and water emission constraints water consumption constraints in the actual optimization framework as opposed to developing it on the back end, but that is something that's currently in the works and not currently in the model. So some overall conclusions from the work that I presented in New England and in Liberia is that information here illustrates how investment decisions change under different stakeholder preferences. And there is a need in our energy planning work for different stakeholder informed models because there are many objectives in power system planning. And the work here highlights trade-offs that different decision makers might make between the quote unquote optimal power system. So while these tools provide insights, there is much needed future work in including other technologies such as solid oxide fuel cells and thinking about, I think, explicitly modeling micro hydro, because I know that there are some different costs for micro hydro compared to the larger hydropower plants, and also getting a higher spatial resolution for looking at the household impact level. But even in spite of those limitations, I think that the work is valuable because we do provide an initial assessment framework for understanding how stakeholders' belief systems impacts the power systems that they build. So thank you very much for listening to me, and I hope that you guys enjoyed it.
Fantastic, and so well timed. We have a couple minutes left, so if you guys have questions, either raise your hand or put it in the chat. I was really struck by the 81% of Liberians don't have access to electricity. That's pretty shocking.
Yeah.
And it just, I guess, and then there's sort of there's lots of other issues, like do they have running water? Do they have, is there transportation? So do you like this whole idea of looking at system of systems? Is that sometimes something that you were interested in looking at?
Yeah, I think that like there's a lot of talk about like the energy water nexus, the energy poverty climate change nexus, right? We know that electricity is not valuable on its own, right? A lot of the benefits that you get from electricity are linked to other things like better healthcare systems, you know, economic development. And so I do think that there is like a need to tie these things to, tie electricity to other systems that are directly beneficial.
Great. Looks like we have a question. Claire, you're unmuted. Or I thought I unmuted you. There you go.
Hi, this was an amazing presentation. Thank you, Destiny. I was curious about the this work and how it looks like it's an SF-funded project, but have you worked with Power Africa, with USAID or World Bank or the C4All programs? Because I know a lot of donor-based projects are kind of trying to do what you did, but they don't have, the resources or the knowledge that you have. And so they could definitely benefit from, this type of work. And I'm curious about your collaborations there.
So I think that's a great point. I haven't worked with Power Africa or USAID. When I went to Ghana to talk with electricity stakeholders in the country, that was more of like kind of on my own. We worked with the Worldwide Universities Network and we got a seed grant to actually think about how do like outer preferences for equality and CO2 emission impact local electricity systems, and how do those objectives from outside forces by these international donors compare and contrast with the actual local preferences. But that's kind of more on my own. So if you know somebody, I'm happy to talk to them. But this is I actually got a graduate research fellowship through the government. So this was kind of like it's like my PhD funding.
We have a question from Katrina.
Hey, Destiny, great talk. It was super cool to see how all of the work I've been hearing about comes together. It's super inspiring. I wanted to ask how sensitive your results were to some of the costs, because I'm like a technical gal, so my dream is for these technologies to decrease in cost through innovation. So for example, like the 2 maps that you had, like if you did any sensitivity to see how those would change with different cost inputs.
Yeah, so for the cost inputs, we had a pretty high cost for the solar diesel mini grids. I think it was like $6,000 per kilowatt hour, which is on the upper range. We did do a cost sensitivity analysis, which I think I actually hid, but now I realize I should have. Okay. So when we're looking, can you see this?
Slide 48. Yes.
Yes. Okay. So we were looking at the cost reduction. So that's the second to bottom row, and so what would be the cost reduction be required to reach like a 20% or 40% solar penetration capacity? And we did solar home systems and PV diesel mini grids. The columns, this is like the low preference and the high preference. And so the interesting thing was we did see a tipping point. So if for solar home systems, if the battery costs fell by like 90%, then all of a sudden you kind of flip-flop your system from having largely centralized capacity to now deploying a large amount of solar generation technologies. And you see the same thing in the PV diesel mini grids. If the costs of these mini grids fell by 68 or 70% in the low preference case, or 65 to 68% in the high preference case, then you flip-flop the system and now you have a large amount of decentralized capacity as opposed to doing like a large amount of centralized capacity. I will say that this is kind of showing you the sensitivity on solar at the $50 million budget case, which I show this one because between 50 and 60, that's when we make the jump to like completely centralized. And so every time you increase the budget, these cost reduction requirements just increase more and more. So that would also need to be kept in mind.
Cool.
Destiny, you have one more question. Are you
Okay.
game to answering? And then we'll have to wrap it up. Offshore wind is becoming more and more important in New England. And with capacity, lower costs, do you think this will be a part of Africa's coastal portfolios?
Oh, good question. I don't know how deep their offshore level is. So if like they're kind of like on the New England side, then I would say probably. If they're more like California, where it gets really deep really fast, probably not. I think that with offshore technologies, they are still really expensive because of the maintenance costs required for like the shipping and that type of like, so like the maintenance costs and overcoming that, like you're gonna have to see a lot more offshore deployment across the world before you will see it in Africa, because they just don't have the capacity to build and maintain those high cost ships. There is a lot of talk in Ghana, at least, so that's where I talk to my stakeholders, so that's why I keep referencing Ghana. So in Ghana, they had a lot of talk about like, how can we use electricity systems to make sure that we are promoting and our own economic development. So if they were able to build a grid big enough to run these industrial plants to build these ships, then I think that you would see an explosion of offshore wind development. But if they can't do it in the house, I think that right now, a lot of countries are like, how can we make sure that we're growing our own economies?
Great. All right, great place to stop. Obviously, you can keep talking for a while. Thanks everybody for joining us. We're honored to have Destiny with us. We've recorded this, so tell your friends, they can come back to it. And our website is metro21cmu.edu. So thanks for joining us. Have a great day. Get outside, enjoy the sunshine. Bye.
Bye.